All right. Hi, thank you for coming. Happy Tuesday. A few reminders for you. First of all, keep working on your project. Um, I've got as well, let me see if I can make this go away. So I put an update for the class where now that we're in week 14, we can list all of the classes and what we're going to do. So today we're going to review recursion and do lab 8. Thursday, we're going to do sorting. And Tuesday, the following, we're going to do sorting lab. This one is fun. Everyone typically has a lot of fun with it, so I'm looking forward to that one. Thursday, the 15th, so next Thursday is going to be project presentations. So keep that in mind. So you're going to have at least mostly working example to be able to present to the class. So you'll like bring your computer up and plug it in and run through the game for the class. And then we do have a final exam. It will be Tuesday of finals week at 3:30. So roughly our class time. Once I write the exam, I will distribute a study guide. I'm planning to write the exam next week. So as soon as I have that information, I will distribute it to you. Keep in mind that this Friday, the minimal working example is due. So this means as much of the code for the project that you've got, I would like it. So treat it like it's your pre-project being due, and I'm going to grade it along those lines. So that was, if this was your final project now, here's what grade you would get. And so I'm making this due mostly so you don't wait till the last minute to get everything working and run into all of the errors. So yeah, so you should be working towards having this working example by Friday. Also, I'm saying this publicly and also in the announcement publicly that the last possible day for any submission, so either if you are turning in things late or turning it again to correct it, the last possible day that I will accept anything is next Friday at 11:59. So anything after that is not acceptable unless we have worked out some situation between us. But you can't assume that that would happen if you don't talk to me. So that's my message. So if there's something that's coming up, it's on you to reach out to me and make arrangements. Otherwise, if everything's going fine, just keep in mind that that's the last day. Any questions or comments about this? Okay. I'm behind on grading. I greatly apologize. This week, for sure, I promise, I will have everything updated. So yeah, so by Friday at the latest, your grade should be completely up to date. Yeah, question.
What percent of our grade is the final exam?
What percent of our grade is the final exam? I don't remember that off the top of my head. Two exams. The midterm and the final are 10%, so I guess the final is 5%. I think that's how that math works. What? Okay. Any other questions? Yeah.
Yeah.
Great question. I think project goes under homework. Yeah. That's what I would default to. Other questions? Okay. So that's where we're at. The course evaluations are also available. I will maybe make time the day that we do project presentations for you to do them in class. But we'll see. So you should do them now if you've got the time. Not now, but outside of class around now. I'm going to give the whole class 1 extra credit point for every 10% of students who complete it. So if all 100% complete it, then you get 10 points extra credit. It's depending on what category you want it applied to, you can conspire amongst yourselves and then we can take a vote. So there's options for like, do you want it applied to the homework, the labs, or the exams? So up to you. Our plan for today, we stopped kind of midway through recursion, so we're going to finish that and then we're going to do lab 8. Any questions before we get started? Okay, checking to make sure I don't have any urgent things. All right, let's resume. Okay. So let's speed through these just to remind ourselves where we're at. We're talking about recursion. Recursion is famously tricky. It's a recursive method is a method that calls itself. So if we're in some function, then we make a call to the same function name. And as long as it calls on a different or simpler instance, we can work our way down to a solution and then propagate that answer back up, and we have our ultimate answer. So we looked at these examples of examining folders or looking up a word in the dictionary. The key idea here is about sub-problems, where the problem to look up a word in the dictionary is the same as looking up a word in that definition is in the dictionary. It's the same kind of process of understand all the words in this definition and go until you understand all the words in a definition, and then it goes back up. So the key here is subproblems. We talked about factorial, where this is a kind of naturally recursive formulation, where if we have n factorial, then we multiply n by n minus 1, by n minus 2, and so on. And so another way to say that is to just say n times n minus 1 factorial. So breaking it down into the subproblem, where to calculate n factorial, we do n times n minus 1 factorial. And then to calculate n minus 1 factorial, we say n minus 1 times n minus 2 factorial. So breaking it down as we go. The breaking it down is really important because that way we don't get ourselves into this infinite loop. We need a way to be able to stop it and have our base case, which for factorial is 0 factorial and 1 factorial are the same thing, which is 1. We talked kind of how this relates to the math side of things, where proof by induction. So I'm going to speed through that part. And then we talked about the rules of recursion, where we always need a base case, which is the simplest possible way that we can solve this problem. We need to always make progress by calling on some smaller instance. I should just take number 3 out. I never know what it means. I got it from a textbook, but I interpret this one as we have to take care to design our recursive solutions. And then once we have worked it out, here's what it does, then we just assume that it works. And then number 4 is we can't duplicate work by solving the same thing in separate calls. And we'll see what that is. Okay, so we together, so we had the sum of n numbers. Let's find that one. So first we did factorial. One of them we did recursively. It's recursive because there's a factorial in the function. And then there's iteratively, where we used a for loop and we just multiplied by I as we went down. We also did the sum iteratively, where we can start at n and work our way down and just add all those numbers up. We can also do sum recursively, where, again, the same idea, where we start at n and we add all the numbers up to n minus 1. And so as we make the recursive calls, that n gets smaller and smaller and smaller until we get to our base case of 1. Then we looked at two examples to print in ascending order and descending order. So for ascending order, it's easy. We start at 1, we go up to n, and you just print I. And similarly for descending, we just flip around the for loop. For descending, it's fairly simple. We print the number and then make the recursive call. And we say, if we get to 0, then we're done. And so I think this may be slightly different from what we had before. I think previously I may have had done here and had the space and the n swapped. So it, like, we kind of get to the same thing. So let's, I think where we left off is we were, I think we were over here. Yeah. Okay, so this is where we're at. While I get set up, does anybody have any questions? Okay, so we'll be continuing in the same Java file because we are printing numbers in ascending order. That's our last example. And then I will talk about a case study, and then I'll let you loose on the lab. So let's first of all convince ourselves that the print ascending is doing its job. And it ends up just being like 2 lines flipped, where for print descending, we print it and then make the recursive call. For print ascending, we've flipped. So where we make the recursive call and then we print. So let's run this just to make sure it does what we want it to, which it does. So if we call print ascending of 5, it prints 1, 2, 3, 4, 5. Great. But the question is, we've made one change, is we've swapped these 2 lines and renamed the function. And so the question is, why does it work like that? Okay. So, here, let me erase, I'm gonna erase this and we'll do it again. Okay, so we're given, let's assume we're given, I'll write PA for print ascending, and we're given n equals 5. And so we go through the method, and I'll write the different recursive calls as we go. Remember when we talked about the call stack, where once we call a method, it gets added to the stack. So when we run a function, it calls main. And then main, if main calls other functions, so maybe it calls factorial. And then once factorial finishes, then it gets popped off the stack. That's how the call stack works. And so this is what we want to write down to help us keep track of where we are. Yeah, there is, I will note that in the lab, there's this idea of a limit here where we can only make so many recursive calls. until it eventually shuts you off and says, no, you're doing too much. So there is a limit because like our computers aren't infinite. We want to be mindful of our resources. So you typically won't hit that unless you're writing a really bad recursive solution. But it is something to keep in mind. Nope, I want to go here. Okay, so we call print ascending of 5. Let me move this over here. And this is the one that we've got. So first we check the base case. Is 5 less than or equal to 0? No. So we skip that and then we make the recursive call. So we add on to the call stack, print ascending of n minus 1, which is 4. We don't immediately go to the print statement after that because we have main and then PA of 5, and then we've added PA of 4. Now we have to process PA of 4 before we can go back to PA of 5. So we have to process this guy before we can go back to where we were. That's the point of the call stack. So we're in PA of 4, we check the base case. We're not there yet. We make the recursive call. So PA of 3, and this repeats. So 3 is not the base case. Yeah, question?
What about that spacing issue from last class?
Yeah, okay. So in here I have space plus n, and here I have n plus space. Let's try to just...
Well, I mean, not the line issue.
The line issue, I think it came from this, where we had, in our base case, we had print ln. And so as we go through the call stack, we'll see when that gets triggered. Okay, so we're at PA of 3. 3 is not less than 0. So we make the recursive call. 2 is not less than 0. Make the recursive call. 1's not 0. Make the recursive call. Hey, we've made it. We've made it to the base case. And so in this implementation, we would print a new line. And so that like moves us on to the next line. And that, so if we do this, then it shoves that line down. That's why. Because we've gone all the way to the base case of 0 and hit enter before we print any numbers. So that's why I think it makes sense to not have that new line and to just say print. Because this is going to get printed first before anything else gets printed. Because that's how we've structured this recursive function. Okay, so we print either, if we're over here, we print a new line, or if we're in what it currently is, we print an empty string, which is nothing. And then we return, which means this gets popped off the call stack. So we're done with this. Now we return to PA of 1. And we were at this line. This line is now done. So we go to the next line where we print the number, or n plus the space. So let's assume we're printing n and a space. So we would print n is 1. So we would print 1 and a space. Right? With me so far? We're done with PA of 1. Now we go back to PA of 2. We left off at this line. The recursive call is now done. So we go to the next line and print the number. And the number is 2. We add a space there. PA of 2 is done. We pop it off the call stack. Now we resume back at PA of 3, where we print the number, pop it. We're at 4. Print the number, pop it. We're at 5, print the number, pop it. So now we have gone down here, and since all of our recursive calls to print ascending are done, then there's nothing else. There's nothing else that main calls, so we're done with the program. So we can pop main and say we're done. Success. Any questions on this one?
It's still doesn't. Oh, you see, if I try, print is, calling print ascending, and then in the next line, print descending, I get the ascending and descending orders on the same line.
Yeah, so that's not exactly what we're going for. So like if we do like this, yeah, that's gonna give us something weird. So what this is doing, so yeah, so the reason these guys for me are all on different lines is because print descending uses a new line when we're done. Otherwise, what it's doing in each line is we print the number for ascending. So the lines go in order 1, 2, 3, 4, 5. And so then in each, it makes the recursive call to start here and print the numbers less than me until 1. So for 1, we just print 1. For 2, we print 2 and 1. For 3, we print 3, 2, 1. For 4, we print 4, 3, 2, 1. And then for some reason, it doesn't do it for 5. I don't know. But yeah, so the goal for this recursive function is not to do that. We just want to print 1, 2, 3, 4, 5. So we shouldn't have prints descending in this function. So if we do that, then we do get 1, 2, 3, 4, 5. Other questions before we move forward? Okay. One of my favorite analogies is, let's say I'm an exceedingly busy person. And so if I'm at my house and I'm on the computer editing a document, and let's say I've got a home phone and the home phone rings, so I go and answer it. I pause my editing and I go and answer the phone. Hi, how are you? Who is this? What do you want? And then let's say my cell phone rings. So I say to the person on my home phone, hold on a second, my cell phone is ringing. Put them on hold. Pick up my cell phone. Hi, how are you? What's going on? And then the doorbell rings. So I say to this person, hold on just a second, someone's at the door. Put the phone down, go answer the doorbell. And if I open the door, this is a recursive process, right? I open the door and let's say the alarm goes off. And then I have to say, hold on, I don't want it to like call the alarm company and say someone broke in. So tell the person at the door, hold on, let me input the code to turn it off. And then once I've done that, then I can deal with the person at the door. Maybe they're delivering a package. Okay, close door, goodbye. And then I go back to my cell phone and say, okay, what do you want? And then once they're done, I can go back to my home phone and say, hi, what's going on? And then once all of that's done, I can go back to editing my file and continue on with my day. That's a recursive process. Lots of things are recursive processes. When I was doing research for my PhD, it's this whole process of writing a research paper where you find a paper that has all of this information, but there's something that I don't understand. So I have to go look up what is this topic and understand that topic in order to understand the broader paper. And it repeats. It's a recursive process. Lots of things are recursive. Okay, and so we mentioned this where we maintain this sort of thing in a stack. And so like we're editing, and then home phone rings, and then cell phone rings, and then doorbell, and then alarm. And then once each one of those is done, we can pop it and move on to the thing just before it. That's how recursion works. Okay, so we talked about that. Do you want to go through the factorial call stack? Yeah? Okay. So I'll call it fact. Let's again say, do we want to start at 5 or do you want to start at a different number? 5 is good. It feels manageable. Okay, so originally we call factorial of 5. So now we look at the if statement. Are we in the base case? No, because 5 is not 0 or 1. So we return n times factorial of n minus 1. So n is 5, and we call factorial of 4. So now we're in this recursive call. So fact of 5, fact of 4. We're in fact of 4, no base cases. So we return n, which in this case is 4, times factorial of 3. Now we're in the recursive call. So factorial of 3 is on our call stack. We're not in the base case. So we return n, which is 3, times the factorial of 2. And then if we're not in the base case, so we return 2 times factorial of 1. Now we're in factorial of 1. We're at the base case. So n is 1. So we just return 1. So the result of fact of 1 is 1. That gets handed back to where we were in fact of 2, where now we can say, I wanted to multiply 2 times whatever the factorial of 1 is. Well, now I know that answer. And so now I can multiply 2 times 1 to get 2. And so then fact of 2 is done. And so then I return to fact of 3, which says factorial of 3 is 2 times whatever the factorial of 2 is. I know that now. Then that answer is 2. So I can multiply 3 times 2, and I get 6. Once we've got that, factorial of 3 is done. And so this answer gets passed up to the level that previously called it. So 6 gets passed up here. So now we can multiply 4 times 6, which 24? 24? Okay. I can't do math when I'm up here. 24, and then I think this was like 120 or yeah. So 5 times 24 is 120. But the idea is each of these math numbers that we got back with 2 times 1, it passes up to the previous level where we can do this multiplication and then return that number to whoever called it. Remember, it's the boss, team, worker analogy, where you can break this big job up into smaller jobs until you give the smallest piece to the intern and the intern can solve it quickly. And then once the intern has the solution, then it goes back up to the team and you can compile all that information and pass it up to the managers and to the boss. And so that's what we're doing here, except instead of working on some big project, we're multiplying numbers. And so eventually we hand up this multiplication up and up and up until 5 times 24 is 120. And then that's what we end up returning for factorial of 5. Questions on that? Okay. So now that we hopefully understand call stacks, let's look at a case where this compound interest rule, where we don't want to duplicate work, where that rule is violated. And this is a very famous recursive problem called Fibonacci. Does anybody know what the Fibonacci sequence is? Kind of? Yeah, okay. So don't worry about it. I'm going to tell you. The Fibonacci sequence is this mathematical sequence of numbers defined in a specific way. So we start with 2 ones, that's our base case. And then to get the next number in the sequence, we add the 2 previous numbers together. So if we start with 1, then we get 1 plus 1, add those together, we get 2. And then we add, so 1 plus 1, we get 2. We add 1 plus 2, we get 3. We add 2 plus 3 to get 5. We add 3 plus 5 to get 8. We add 5 plus 8 to get 13, and so on. So we can continually build up this sequence. So let's implement it. This is, you can also like copy and paste this part that we're going to do into the lab because that's part of the lab. So we know how to write recursive solutions.
Wait, do we put this in the new class or in the same class as last time?
I'm keeping it in the same class as last time, just so all of the recursive code is together. Public static. Let's make it a long, just for fun. Actually, let's make it a big integer so that we can practice for the lab. Okay, that's the return type, public static.
What is big integer?
Big integer is a Java type, a type that Java has defined. And once I give it a method name, Fibonacci,
How do you spell
how do I spell what?
it?
1 B, 2 C's. Fibonacci.
We have to import big integer.
Yes, that's correct. So if we do that, then we've got an error because we haven't implemented anything yet. So we know how Fibonacci works. Fibonacci has 2 starting numbers. Here's the point where we make a decision. So I've made the decision in the lab that I call the 0th Fibonacci number to be 1 and the first Fibonacci number to also be 1. If you look this up on the internet, there is a chance that you will see maybe the 0th Fibonacci is 0 and the first is 1 and the second is 1. This is just the decision I made. It's just off by 1 of
So
how are we counting.
what do we,
I will go back to it in a moment. This is what I've decided. The 0th is 1, the first is 1. That's where we start. So I've had my parameter is a capital I integer to helping me with this.
integer, what's that?
The variable name is n. Because the goal for this function is to find the nth Fibonacci number. That's the goal. So if we go back to our sequence 1, 1, 2, 3, 5, 8, 13, let's say the third Fibonacci number is 0, 1, 2, 3. The third Fibonacci number would be 3. The fifth Fibonacci number in this counting is 8. So this is n, is kind of like the index for the counting. So give me the nth Fibonacci number. That's what the goal of this function is. Okay, so first off, what's our base case? Where does the sequence start? Two ones, right? So we start with two ones, the 0th and the 1st. And so since we're counting, our input is like the nth Fibonacci number, that means if the n is 0 or n is equal to 1, so similarly to what we did for factorial, then the Fibonacci is 1. So I type that, but now I get a type mismatch cannot convert from int to big integer. So let's represent this as a big integer. And the way that we say the number 1 is there's a few ways to do it. We could do big integer dot value of and give it the number 1. So this is kind of wrapping it around and saying, I'm giving you an int, convert it to a type big integer. And the reason we use big integer is that these numbers can get very, very big, much bigger than int or long allows us to. So this is one option. Another option is to just say there's some static fields that belong to big integer of capital ONE1 or 10 or 2 or 0. And so I could say big integer dot 1 as well. Okay, so that's our base case of if we're looking for the 0th or the 1st Fibonacci number, our answer is 1, always, forever. Now we need to make our recursive call. So based on this sentence, talk with your neighbor for 30 seconds. What's our recursive call going to look like? Fibonacci of what? Go for it. Discuss.
Take the function, copy it, make another function with different arguments.
Okay.
The first argument is the current number, and the second argument is the next number. And then basically in in both functions, you return the, or hold on, then you return, Fibonacci. And then have it be, wait, no, never mind, scratch that, never mind.
Okay. Thank you for trying. Appreciate it. Other ideas?
Would we still use, instead of current and next, would it be like value and then like what n is? And so basically it kind of be, well, like it'd be Fibonacci val plus n. Or like Fibonacci n or whatever.
Yeah, so we need to somehow make the problem smaller at some point.
We just use n minus one.
Yeah, so there's some notion of n minus 1. There's also another expression in terms of n that I'm looking for. So let's say I'm looking for the 3rd. In order to find the 3rd Fibonacci number, I need to know the 2 previous. So I need to know the 2nd and I need to know the 1st, and I add them together. Right? So our basic formula for Fibonacci is I need to know what this Fibonacci number is, and I need to know what this Fibonacci number is. So we can have two recursive calls if we want to. So we can just say, in general, fib of n is equal to fib being short for Fibonacci, fib of n minus 1 plus fib of n minus 2. So to find the third Fibonacci number, I need to know the second, and I need to know the first. And so I know the first, that's 1. And so I just need to find the second. And so the second is the first plus the 0th. And I know what both of those are. So I can take that, add those together, pass it up to say, this is the second Fibonacci number. And then I can finally get my answer for the third. Are you confused?
It's like whatever the n is.
Yes.
Like that n minus 1 will now become like n minus that n, and then it's gonna be n minus 1, n minus 2. Keep repeating until you get to 1 or 0.
Other points of confusion? Cool. Okay. So we know the general form of this is what we want to do. So let's implement that. So in general form, fib of n is equal to fib of n minus 1 plus fib of n minus 2. So that's kind of what we want to do. So we want to return. So we have been called with Fibonacci number n, and so we want to return Fibonacci of n minus 1 plus Fibonacci of n minus 2. Yep, it would help if I spelled out Fibonacci. There's a small change I need to make here, but this is the general idea. Where we call it with the one previous, and then the one previous to that, add them together, return that. The change I need to make here is that big integers don't know what to do with the plus operator, but that's okay. I can just use a method. So big integers have a method of to add two things together. To add two big ints together. Let's say we've got A and B. We say A dot add B. And so so we'll replace the plus with Fibonacci n minus 1. That's a big integer, so we can say dot add and then n minus 2.
Fibonacci n minus 1 dot add Fibonacci n minus 2.
Correct. Cool. Looks good. Let's test it. All right, I'm going to go down to the main for a second. So print Fibonacci of, let's say, 5. And I believe 5 in our numbering should be 8. So Fibonacci of 5 gives me 8. Hooray! We got it. Let's try the 10th Fibonacci number. 10th Fibonacci number is 89. What about the 20th Fibonacci number? 10,946. Let's keep on going. Huh. Something's going on here.
What number did you enter?
50? And so what's happening since the little red square is illuminated for me here, this says that it's still going.
Entered in here.
Not necessarily. So sometimes, so far we've learned that this means that we've entered an infinite loop. But let's talk about what's really happening here. So I'm not going to terminate it. I'm going to leave it and see if by the time I'm done explaining it, it'll have finished. Because it will eventually finish. That's the thing. I can keep giving it bigger and bigger and bigger numbers, and it will eventually finish. But the problem here is that it's not doing this efficiently. So I don't have that drawn. So here's what's happening. We want to calculate fib of 5. What we're doing here, we're actually trying to do 50, but let's take n equals 5 for simplicity's sake. No, actually, let's do 50. So fib of 50 calls fib of n minus 1, which is 49, and n minus 2, which is 48. Bless you. Fib of 49 calls fib of 48 and fib of 47. Fib of 48 calls fib of 47 and fib of 46. Are you seeing the problem yet? What is the problem? It keeps on going.
I guess an expanding number of recursions.
So yeah, so I mean, this is the case when we make 2 recursive calls, is the recursive calls have to go somewhere. But there's something specific about these recursive calls. They're overlapping. Yes. So let's see if can I come up with another color. Let's take, no wait, that's not color blind friendly. Wait, red and, yeah. Let's take red and blue, maybe. Okay. So already I can see 2 instances of 48. So we've duplicated work where we're trying to find 48 twice. Even 47 we find 3 times. And so as this process continues, as we continue making these recursive calls and breaking it apart, there's overlapping work that's being done. So we're violating this compound interest rule where only do one thing at a time and don't do anybody else's work as well. This makes sense for the management perspective, where you don't want to have 50 people working on the same thing, because then you've got 50 different instances of the same task. You want to have, for maximum efficiency, you want to have each person working on their own task. So this is the problem, where there's overlapping calls. And so we're doing the work of calculating fib of 48 twice. We're doing this work of calculating fib of 47 3 times. And it keeps getting bigger. That number of how many times do we compute this gets bigger as we go through this tree. So that's the problem. Let's see. We eventually finished. So like I said, it eventually finishes, but it's just extremely slow. So the job for the lab is make it better. And so I have outlined in the lab, let me pull it up. So I walk you through the strategy to fix this, and I'll tell it to you in general, where the idea is that outside of our recursive function, we have something called a map. Do you remember dictionaries from Python? Okay, so dictionaries or maps in general are this idea of a key value pair where there's something like, what's the best analogy? I feel like dictionary, so like dictionary, a literal dictionary is kind of a good analogy where you have the word, that's the key, and that maps to its meaning, the definition, that's the value. So the idea is that you access something by the key and that gives you back the value. So you're going to use a kind of map called a hash map to store this. So where we have, let's say this is the key, this is the value. And so the key is going to be n. So like 0, 1, 2, 3, and so on. And the value is what's fib of 0? What's that number? And so as you go through your recursive solution, you're going to check. Instead of making all these calls, once we get here, we're going to check. Have we solved this yet? And we'll know if we solved it if there's an entry for it in the map. So it's like we've got a sheet of paper, and as we make a calculation, we're writing it down on this separate sheet of paper. And so once we come across a problem, we ask, have we done this already? Let's check. If we have done it, then we don't need to do any more work. We can just grab that and say, here's the answer. Job's already done. If we haven't, then we do need to make the recursive call. So it's just adding like a gate to check, have we done it yet? And that way we don't have to duplicate all of this work. So you'll have practice with this twice, once in Fibonacci and the other in Pell numbers, which is kind of related to Fibonacci, just slightly different. And this process is something called memoization. And it's part of something called dynamic programming, which, if you go on to take 374, is what we're doing right now. So it's kind of the next step after we learn recursion. How can we tailor it to fit our needs so that it can still be efficient and solve these complicated problems, but not like pollute all of our recursive calls? So this idea of memoization, not memorization, memoization. Memo, like as we, like in the office, how there's like memos that get sent. That's the idea, where we're writing a memo of, oh, this is the 60th Fibonacci number. Now I don't have to calculate it again. So that's what we're going to do to solve this problem, is we are still going to do recursion, but in addition, we're going to write things down. Okay, so recursion can be seen many, many, many places. We saw it in factorials. I have a link here to a cool story for binary search, which involves, so binary search, let me say what this is first. So let's say we have an array full of stuff and it's sorted. Then to find something in the array, so let's say we've got the numbers 1 through 100 and it's all sorted. Let's say we want to find the number 74. Well, we could, so if we know like the index, then we could just go to the index 74, but maybe it's 50 to 1,000, or there's some offset, or there's not every number from here is included. Maybe we have like 62 and then 64. So maybe there's numbers missing, right? But it's still sorted. So the question is, how can we find 74? The way we do that is binary search looks at the middle first, and we ask, is this middle number greater than or less than 74? if this middle number is greater than 74, let's say X, let's call it X. If X is greater than 74, then we've gone too far and we have to go back. So we have to go and search this half. This is a recursive process. Now we're in this half of the array and we're doing binary search again, where we start at the middle and we look at this number. So let's say it's 60. Is 60, how does 60 compare to 74? It's smaller. So we have to look at this part of the array. So we have to go right. So the idea with binary search is go to the middle and ask if it's less than or greater than or less than the target or whatever we're looking for. And then if the target is less, then we go left. If target is greater, go right and repeat. Where we start at the middle, compare them, go left, go right, repeat until eventually you're going to find the thing that you're looking for. Okay, and so the cool story with that is that someone had their bicycle stolen and there's a surveillance camera right above it, and they went to the people who own the camera and they're like, hey, can you look for see who stole my bike? And they're like, there's so much footage. How can we ever find it? And this guy's a computer scientist, so he's like, well, just use binary search. So choose a point in the middle. And like, I know when I parked my bike there, or like roughly the day, and then up till now. So choose a point in the middle, see if the bike's there. And if it's not, then go back until you find a point where the bike is there. And then you have your starting points. So like, oh man, I'm not good at drawing a bike. And so you repeat this process now. So where the bike is here and go in the middle and see, is the bike there? If it is, then someone stole it later. If it's not there, then someone's stolen it already. So it's this way to efficiently search for something in this long string of options. There's also examples like fractals, like here, and games like the Tower of Hanoi, which is a game where you've got these discs and you have to move all of this stack to from the first pole to the third pole. But as you go, you cannot place a smaller disc. Or no, you cannot place a larger disc on top of a smaller disc. So the question is, how do you do that? And so one way you can do that is with recursion. It also has applications in cryptography, like can you compute modular arithmetic or greatest common divisor, or testing whether something is prime. And I will reiterate that first when you're designing these recursive solutions, first make sure that you have a base case. So that's going to be the question that I ask you when I come around when you're having trouble is, what's your base case? The other question is, what's your recursive call? And are you sure that you're making it simpler each time? So how are you progressing towards the base case? That's what I'm going to ask you. Since we've talked about Fibonacci, keep in mind whether there's any overlapping work being done. This kind of is up to interpretation. For this lab, all of your methods should absolutely be recursive because we're practicing. But just keep in mind readability, where sometimes the recursive solution is the most simple and elegant. Other times it's better to just use a loop. And Then we'll briefly talk on Thursday about algorithm analysis and why we can't assume that a recursive call just does it like that. So there's other considerations to keep in mind. Okay, I've talked a lot. We've got about half an hour left for lab 8. So I'm gonna pause recording and then put you into groups. I've gone over, so I'll put you in the groups. Let me just talk about the lab. So Fibonacci, you have the first one is to implement naive fib, which you've got that code already. Great job. The other 4 and 5 is to do this memoized version where we're storing this information. So I have a lot of code here that if you read carefully, I give away the answers. And so then I've got a main method in the code, so you can test it there if you want. And then just run the appropriate tests. And then do the same kind of thing for Pell numbers. And then the third problem is on palindromes, where palindromes are words that read the same backwards and forwards. So race car, read backwards is race car. So how can we figure out that a word is a palindrome recursively? Questions before we break up into groups? How do you test it? Test what?
You said there was a main method.
There will, yeah, there will be main methods in the, so in main, let's take Fibonacci. So I've got a main method, there's a main method provided for you. Use that if you want to just call the method and test it. But the thing that the grader will do is they'll look at the recursion test.java. Okay, let's split you up into groups. All right, we're at the end of class time, so be working on this. So we're not going to have time in class to go over it again. So exchange contact information with your partner, emails, phone numbers, whatever you need. Set a time outside of class to work on it. It's tentatively due Thursday. If you need more time, I can hear arguments until Tuesday. Let's see how we're feeling on Thursday about it. If you're really lost and confused, come to office hours. I have office hours tomorrow, 10 to 12, or by appointment. Just use that link and set up a time. Happy to talk it through with you. Recursion is hard. But first, try and work through it with your partner. See if your partner understands what's going on. And then if you both are confused, then come talk to me. Be working on your project. Be working on Lab 8. Thank you, and I will see you on Thursday.